Rise over run, exactly. So we have this graph. This is our mass. No, it's not. This is our volume. This is our mass right here. So if we have rise over run, what is our rise in this case? Grams. I hear grams. So grams is our rise. So then what's our run? Milliliters, right. So I can't even remember if we did grams. I think we did. I think it was grams and milliliters. But yeah, so we're calculating this. What does this look like? A formula, right? But what do these units in particular remind you of anything?
Density.
Density. There you go. Perfect. So the slope of our graph here is what?
Density.
There you go. Perfect. So we're going to be doing a little bit of calculation with that, and then after that, we'll be doing part 8, just going back through calculating percent error. Does that make sense? Cool. So we're just going to get at it. If you need questions, me and Mr. Hobbs will be going around and just checking up on y'all and see if y'all need any questions from us. Yeah. All right?
You didn't want to.
You good? Ready?
Yes.
Perfect. Go.
Do what?
Sam, let's see. You good there? Did you already calculate it, or did you?
I think I did.
Let me see. I'm just like, I see the best fit.
No.
So you, I think what, so you put density as mass times volume. I think that's the name. So what's the actual density?
When we do a graph on this, we want to do the best fit straight line. Like dot.
There you go. Yeah, right. Because we just did the
So
well,
you
it's not
use a
already,
ruler right here.
but we just did that. So like rise over run, remember? So if we're taking it off the graph off this, and you know that the slope is the density, then that's our density. That makes sense? Yeah. So you might want to redo those. Because that's also another thing. Is like if you can see that your densities are going to be different between the two, that means you're probably wrong.
So you can erase, I don't know if you want to erase the other one first or.
75, and now you've got 21, I was like, something's not right.
Yeah. Exactly. Yeah. So that's always a good check. I mean, if y'all remember, density is an intensive property, right? So if your density numbers are extremely off from each other, you've probably done something wrong. Yes.
For this one, I got it to the opposite
So are you talking about for which part? Sorry.
we're looking for,
Density, right?
Your points are pretty good.
Yeah, Maxwell by 1. So you
Yeah.
divided 2.35 by 3 milliliters, and you got 0.783.
but like, these ones I kind of got too because.
Okay, why you multiply?
So that comes into our error, right? So I would make sure to write it as is. They're pretty close to each other, so it's not like you're calculating your density right. The main thing is just making sure that
Equals mass
so
times
there's not
volume.
so you're not
Mass.
calculating density right. Is that it's just that because of the way that the measurements came out to be, your answers are going to be not 100% accurate, right? Because we're not humans aren't perfect. We're not going to be exact on everything we do. And like there's going to be so many different factors that come in the way of that. So that's kind of where our accuracy and precision calculations come in, which
Now,
I
if you
think
apply,
I need to look at the
like
sheet
you,
again.
the ruler on the drawing line, I mean, I know that it almost looks like it's on dot to dot. The other point right there.
So yeah, that's where our percent error stuff comes in, right? So go ahead and make sure that you
Yeah, but
just
where is
like
the actual
put
point?
down your density and then start
Where's the
calculating
actual
percent
point?
error from there, right? So do you know how to calculate percent error? Because the formula is right on the results screen, right?
Okay,
So yeah, so that would, pretty much percent error shows us
So then you just want
like
to use
how
this,
far off
and use
something
this,
is, right? So
line, and it's
you can
gonna
kind of
be
use it as
close
like,
to
oh, okay, so my actual value is supposed to be, so I guess that's part of the formula too, right? So you have your calculated value, so, and then for your correct value, you just use that on the board, right? So then you go from there, that's how you calculate percent error. Does that make sense?
Yeah, that is good, yeah. So
Yeah.
now your slope, slope calculations, let's just show it like this. Okay, so you have your graph, you got your volume down here, and you have your mass, and then you draw this. Here's your line with your 4 points on it. Okay? You do not have to use one of your 4 points. You can use any point. Okay? You can use anything that, and if one of your points is not on the line, you want to make sure you don't use that point. You want the points that are on the line. So, but I want you to show, and what I always do is I just find one that's going right through a vertex of my graph, so I know exactly what the value is, and then just show, this is your rise, and this is your run, just show it right on the graph. And then put out here, rise over run, and then put in your actual values. But okay, so whatever it is, so find a point that makes it easy so you can be more accurate with that. And just go ahead and do the calculation directly.
I totally forgot about the right special.
Well, that's fine.
See,
This. The right.
Yeah, or-
Right on the line piece of where you can use
Or
it.
you can just like, see how that point goes right through a vertex right there? And then you can just kinda, I always like to pick these.
So yeah, his point, if there's a point that's like
Because
not
now I
directly
know
on the line, then
that
you
my
might
run
wanna
is
retry
exactly
it.
7.
You might get closer values.
And my
Again, you still might
rise,
be a little bit off because of your given area memory and whatnot.
the
but-
rise,
Yeah.
okay, this is 5, this is 6. This is basically 5.66.
Okay.
Yeah, you try and spread them out more, don't try to go right next to one another.
Yeah.
The more spread out, the more accurate you're gonna get. If you put just super close, you sometimes get messed up.
They only need to take one density, or do they need to take multiple slope calculations, right, for accuracy and precision, or?
Well, that's, what they're gonna do, I mean,
Or is that part A?
okay, for part A, they can do the accuracy and precision based upon, they measure the density to the weight.
Okay.
So
Oh,
how
okay.
close how close those two units are to precision, how close they are to the right units is the accuracy.
Yeah, yeah, yeah.
And then for part B,
I wasn't sure if we were doing that for part B or not, so.
for part B, we can do accuracy is how close the slope is to
Yeah.
the density.
Okay, yeah.
Precision is how close your dots are to the line.
Mhm.
I got 10 things, that's still
You got what?
10, 10 grams and 10 millimeters.
Okay, now are you counting squares or you counting what this represents?
Squares.
Okay, don't count squares. Okay, so this is gonna be right here in the middle, so that's gonna be 3.5 is gonna be a rise. And your run is right here, it's gonna be 4.33. Well, actually though, we gotta go the difference between these two here. Okay,
Water displacement, so,
so again.
do you remember
this is why I
the
said
virtual
just
density lab, how you
this.
found the water there, or the volume there? You basically, remember you put the thing in the block, and then you found the final volume, and then you kind of
Based
subtracted the
upon
initial
actual value,
final
so
volume.
you're gonna be going right here,
So,
5.5
It's
minus.
essentially the same concept, right? So it's pretty much doing that, what you did in the virtual lab, but like in real life. Does that make sense?
You have
Is it filing minus initial?
1, 2,
Yeah.
3,
And that's it?
4, 5.
Mhm. Yeah, that's all you need.
4, 5, okay. So each one is 0.2, right? 4, 4,
So,
point 5, 0.75.
yes, yes,
So-
Okay,
That's
So
the
this is
density that you
0.75.
found from your graph, right?
this is 5.5.
Okay.
This is
So,
all-
let me find the results sheet so I can make sure exactly
Oh.
what's going on. Calculating here. It's not you. Where did I put mine? I put mine somewhere else, anyways. Being with it. your density, right? So what I would do is find how accurate that is based on, like how accurate it is to like what it's supposed to be. So how do you think we could do that? How accurate this density is to the alcohol?
Oh.
Check your results sheet. Did you only get, oh, it's on that, it's weird because it's stapled on that side. That's right. I remember that from, other side, flip it. There you go. So that's what you're, going out. So you found that and then you wanna find your percent error for each, right? And so you have the formula right there. So you have the calculated value, right? 1.24. What do you think the correct value is?
The number that I found.
The number you found? So the number you found is this, right? So you get that.
I was thinking one of these.
So think about what that stands for. So this 1.24, it's for, what is, sorry, one more time. I totally interrupted you. What does it stand for?
Density.
Density of what?
The metal we put in.
This is the alcohol chart, remember? So in that case, this is the density of what?
The alcohol.
Yeah, so this is the density of alcohol, right? So we calculated the density of alcohol, right? So
Okay, which
what would be the
equals what?
correct value?
The amount.
Divide it out in the calculator.
So this is the density that we calculated. So if we wanna know what the correct density is, what would we just look at?
Am I running to the hundreds?
Well, how many sick days, yeah, probably based on your
Just look
graph.
up,
1.54.
see,
1.54.
Density of alcohol.
there you go, yeah. So that's the real value, right? So our calculated value is what we found there. We use that, we usually plug in that value. Yeah, exactly. So it's usually your calculated value minus your correct value over your correct value times 100 gets you percent error. And then that will show you about how accurate your measurement is to that.
To
Well, you
whatever
are, but I mean,
measurement is
you said
the exact,
1 point. Zero.
measure.
See, so what you calculated is your estimated,
Just see.
right? So that's your calculated value.
Mhm.
The exact measure
So we know
is the 785. That's the one that's logged, right? So that's why people, scientists across the world have done alcohol density measurements and have decided on that
This
number,
one is 1.
you know?
So this is 3.3.
So yeah, no problem. And that'd be accuracy. So that's accuracy.
I'm not
What do you
sure
think
where you
precision
guys
would
were
measure?
getting These guys from, you
Did
said
you go over-
3.5.
Have we done
This is
precision
not
yet on this one?
4.5.
I don't know. I don't think we've gone for precision yet. So just make sure to go through the calculation first and we'll go over precision.
So, and then
Yeah.
your run, this is 5.5.
You raised
This
your hand.
one
Oh, I
is
did?
0.75.
I'm stretching.
Maybe, okay.
Well, I do have a question. I wonder, am I running to the one sig fix because this has one, did it just three?
So the volume of your alcohol, you have 3579, right? But
They're on one.
what did you put that alcohol in? Like when you measured out to 3, how did you measure it? And that's not,
The 3.0.
3.0.
You
Oh,
sure
sure.
you plotted this and
Number
see?
for uncertainty.
So I guess, do we not have that?
I think
So you're
you-
right,
you're
but remember that the one that you measured in for that alcohol was to the
Yeah.
10th place, right? So your
Mass is
measure of certainty would actually go out to
2.57
what?
first.
The hundredths.
Yeah, there you go,
Alright.
yeah.
So that'd be 3 sig figs.
Yep.
Mass is 2.57, which is what you have out there.
So rise over run, right? So
Five is right here.
did you count block, so
So 7 is 5.9.
let's see, you calculated density with your points, right? So now I want you to, instead of doing that way, try calculating it based off your slope, right? So you calculated your slope is rise over run, so how did you get that? Just from, Okay, so yeah, you did that right. So this is kind of like to show you what some of the best fit line versus that. So it might have just been the way that you wrapped it while you got the 1.5 on there, but that's okay because this is kind of like part of the lesson is to learn how accuracy works. So now we're gonna go into the percent error. So you've already done it with this with your density slopes there, but I would do it with the slope that you found, right? Because remember, what is that slope supposed to represent?
Here's one issue.
Right? Yeah, so it represents the density with your best fit line. So
1, 2, 3.
if we assume that's the density,
1 to 2.
try and calculate percent error with this density versus our normal density, if that makes sense. Yeah.
I'm just gonna try and see, because somewhere around there, there's something screwed.
All right. Yeah.
First one.
So yeah, remember percent error, right? So what is that going to be in?
Percentage?
This is
Yeah.
gonna be
So 57 point
3.5.
well, I guess would be 58.0, but
If I went-
rounding,
if I
right?
did this.
Yeah,
down to
58.0%. So that's how accurate you are based
I
on
know I might run.
based
it's
on
gonna be
the slope that you found off this line.
Like
Make
all
sense?
the way down
Yeah.
to 0.
Yeah. See? That's it.
At that point,
No, okay.
this is
Yeah.
3.5.
All right. That's it. Yeah. That's it for part B. So now you want to double back. Once you're done with that, double back to part A and go through these calculations.
3.5 divided by
Is that the same
4.33.
calculation?
So do the part A calculation. So that's going to be where you compare the two different methods of density that you did for the metals. Because part A was the metals, part B
I'm not
was
sure.
the alcohol.
Okay.
When
Yeah.
you pick these points, we were doing
Hmm?
something.
You've got an old sheet, that's why, because we took that out. So don't worry about that.
Oh.
Yeah.
Like I need to do 7 for the
Sorry, what was that?
like I need to do 7.
Okay.
Uh,
So I wanna
you
just
need
kinda
to do
use
7
these 2
for
points
the
to figure it
alcohol,
out.
right? Because you still have one of
Because
those.
this should give you the exact same line,
So,
should give you the
you
same.
need to
points.
calculate percent error though.
Okay,
So which one is, what's the correct?
so we know that this is 0.75.
Right there,
Oh.
0.75, yeah.
And this is 3.5.
Well, it's like this,
And that's what I understand was if you get to 4.5.
That's
3.5 minus 0.75 is gonna be 2.75. So my rough rise is 2.75, and my line is from 1 to 4.33, so it's gonna be
So
3.23.
you got that done, perfect.
I think,
So
I'm
you
gonna
go
look at this, 'cause I got,
2.75
like,
divided by
the
3.33.
Yeah, so remember, you're working 1.5
It's gonna be.
and minus 0.75 or something.
Reality
So
is
you're
it's
basically
using
off
this
by a
whole
whole
thing is gonna
thing,
be-
so yeah, the percent error is gonna be bad.
But.
So yeah, don't worry about that, that's accurate. So I think the
You just gotta
problem
make
with
sure
the reason
just do
that you
your
got
Y2
that
minus Y1
is so look at your
minus that.
best fit line. Where does your best fit line start?
Yeah. Okay,
Yeah, it starts at 0 and like 0.5, right? So if the mass of something is 0 grams, what's the
okay,
volume?
if you have your graph done and you
Yeah,
have
so
your slope
I
calculated.
think what you need
Oh,
is,
yeah.
yeah, it
Get the
starts
math,
at 0
the
and then you
density
can
of
go.
your
That's probably why
solid
you
in
got a
the
little
two
bit
different
of
ways.
that.
So it should be 4
Yeah.
density calculations. Well, actually, you only did one solid, right?
Did you finish with part B or part A?
Yep. Mm-hmm.
How do we, just kind of, cause you don't have this graph for that, to calculate this.
So for part A, you just use the density comparison. So right, for part A, you measured, go back to your part A video, right? That's your, yeah, so, your part A video should be this, so you've got the masses and the measurements for volume, right, here, for both of these. So, you have the method to calculate density, right? What would you do with those?
Just do the mass divided by the volume.
Mhm. Yep. So yeah, you don't need the graph for part A because you haven't made a graph for part A, right? You already have your,
Original
yeah.
or final?
What do you think?
Initial?
So think about this. So, do you remember the virtual density lab, right? So you remember how you got the volume of the whatever block that you threw in?
You measured the water, the amount of water when you put the block in.
Yeah, right? And so it moved up by a certain amount, right? So what do you think, what that amount that it moved up represented?
The density of, or,
So, so like, remember, so it's like I had 100 liters, right? And you threw the block in and it raised up by like 5 liters or something like that. So then what can we assume about that block if it raised up by like 5 liters?
It was 5 liters.
Yeah, the volume was 5 liters, right? So using that same logic with the water displacement, what would be the volume that you would use of the metal?
So you just do whatever metal you did. Oh, final.
That's fine, I'll be close though. Remember, we had 30 milliliters, we went up to 37.5 milliliters, or 29.5 milliliters, we went up to 37.5 milliliters, so how many, or how, what am I gonna say? What's the volume of the metal, if we put the metal in, right?
8.
There you go, yeah,
Right.
yeah. Exactly, yeah, that's it.
Say pigs. Don't say pigs.
Yep.
Eight what?
It what?
Sir?
Well, say pigs, and that, what
True.
two volumes are you subtracting?
The volume of the water.
I know, but what, to what number? What are the actual numbers?
No, not this one right here, yeah.
29.5 and 37.5.
Okay, so you have one decimal point, right?
Yes, sir.
So how many should your answer have?
1.
One decimal point.
Mhm.
So instead of just saying 8, 8.0.
Looks like you're starting A, nice. You got everything figured out in B, straight up confident, okay, good, 'cause I know you said you hated math, so. Wanna double check.
We didn't post anything in the classroom for today.
No. It's not partially on me, but. Mr. Hobbs, should I just stop the video?
What?
Should I stop the video since it's not really?
Well, I mean, I was just thinking that they could hear different conversations that were
Okay.
going on, but,
Yeah.
I mean, I don't know, isn't everybody getting close to being finished? Cause you're gonna start talking about accuracy and precision, right?
Oh, yeah, sure. Yeah.
This one, if they have, like, the grams per milliliter is different than grams per centimeters.
So, basically all that is that, so 1 cubic centimeter is 1 milliliter. It's a direct conversion, so you can write that as either or.
Oh, okay.
So, yeah, that's just a unit conversion, so it's, that one isn't as bad as the other ones, cause it's really just like, boom, done. Yeah. The main reason that's there is that it depends on, solids are more used in centimeters cubed, whereas like liquids are more are y'all on part A calculations? Done, close to finished,
I'm close.
close. Alright, I'll give y'all like 5 more minutes to get those done, and then we can go ahead and go over them, and then we can talk about accuracy and precision, because those concepts are important, so, yeah. Where are we? Are we done? Yep, yep. Not done? Not done. Done. Okay. So let me go here. I don't know.
So when you like calculate value and correct value, what are they referring to?
Alright, so calculated value, what do you think that means?
The ones that we calculated.
Right. So then, correct value, think of it more of like the recognized value for that. So just look up for a second. You see on the board, you see those values right there. So that would be like our correct value, because those are ones that like scientists have, all or whoever across the world has decided that and they measured correctly that was the exact density of those items. So basically, percent error is caring about like how close were your measurements to their measurements, you know?
Let's go ahead and go on.
Yeah.
She just finished up, she's gone.
Okay, perfect. So yeah, we'll go ahead and go over these questions real quick. So we're gonna start with part A. So let me get to that table and write it out. So So basically for part A, we got a metal and we measured the density 2 different ways, right? So, we just need one person's data for this part. So, who wants to give me their data? Madison, you had your hand up first. So, what metal did you use?
Brass.
Glass. Wait, brass. My brain heard glass, and I know that's not right. Anyways, what was the mass of the first one?
68.16.
68.16, okay. Second mass you measured?
68.071.
Oh yeah, this is also the, where we used the different scales, I do remember that part. Alright, and then the length?
4.95
4.95. 4.95 what?
centimeters.
Thank you. Alright. Always make sure to put those units down, because they'll trip you up, especially when we get further on, when we start doing more and more calculations with them. If you don't have your units right, your entire calculation is going to get messed up because you're going to forget, and then you're going to have some weird unit combinations. So always remember your measure or your units. All right, what was the width?
1.25 centimeters.
All right, 1.25 centimeters. That looks like a 6. And last one.
Height.
Your- Yep.
1.25 centimeters.
1.25 centimeters. Okay. Perfect. And we'll go ahead and get the volume that you got for the metals through the water displacement. So I'm gonna unfortunately have to slide this out of the way. Goodbye. Very well done graph. Alright, initial volume, what'd you get?
40 milliliters. 40.0 milliliters.
What was that?
40.0 milliliters.
40.0 milliliters. Okay, and then your final volume?
48.5 milliliters.
48.5 milliliters. So then the volume of the metal?
8.5 milliliters.
8.5 milliliters. Okay, so now we are going to go through and do the densities. So this is kind of the method to show right now, but once we get to our percent error, we'll kind of go through from there. So densities, where am I going to put these? Let's do here. Alright, so density with the measurements, we'll go through mass 1. Oh, excuse me. So this will be mass 1, volume with the ruler. So what did you get for the density on this one?
I got 9.51 grams per centimeter.
9.51 grams per centimeter what?
Squared.
Squared? Think about it. You got length, width, and height, right? How many different measurements are we working with today? Cube, there you go. Alright. So then we'll go our density mass 2 volume water. So what'd you get for this one?
Oh, 8 grams per milliliter.
All right. 8.0 grams per milliliter. All right. So now we're going to do percent error here. So yeah, I guess this is going to be Madison show for part A, but that's okay. We're going to talk about it for everybody so we can know what we're working with accuracy and precision. So what did you get percent error for density? Part 1?
18.75%.
18.75%. So is this to the right number of sig figs? No. Cooper, what is the right number of sig figs?
12.5.
So you got 12.5 here. So what that means, right number sig figs is how many?
3.
3, there you go. So this should actually be 18 point what?
8.
8, perfect. Yeah, always make sure to remember your sig figs. All right. And for the second density, Madison, yes?
Why is it 3?
Why is it 3? Good question. Cooper, you got yours in 3, so why is it 3?
Because 3 was the least accurate number.
It was the least accurate number, right? So remember for this one, we're using these calculations over here. Our mass for this one was the 4 sig figs, right? Our volume over here, 3 sig figs. And given Cooper's answer, again, 3 sig figs is the least accurate between these two, so our percent error is going to be 3 sig figs.
Yeah.
Thank you for the plant question, really appreciate it. The secret question come in to help us out here, just to make sure everybody understands that. All right, and so Madison, density for your second part, what'd you get? Or sorry, percent error, what'd you mean? What'd you get?
0% error.
0% error? All right. 0 point what?
1.
So 0 point,
0.
let me check just to make sure. So, remember this is the water, right? So first off, let's go back to this. So, initial volume, 3 sig figs, final volume, well actually no, this is the accurate measurement, so these are right. But, remember our volume of the metal that we got from here, what do we get?
8.5.
8.5, so how many sig figs is that?
2.
2 sig figs, right? And then for our mass here, how many sig figs? Olivia, how many sig figs are right here? 4? 68.071.
Oh, 5.
5, there you go, perfect. So, what's our least accurate measurement?
2.
2, right? So our percent error should be
Not
0 point, you got 0.2, what did you get, Madison? Past the 0, so 0 point what?
Oh, no, I was wrong about that. I don't think it's 0% error.
You don't think it's 0% error? Okay, so this gives us a good idea to calculate this then. Awesome. So, the density that you got here, 8.0 grams per milliliter, right? So, let's look, use brass, right?
Yeah.
Brass, 8.0 grams per centimeter cube, or cube centimeters. So, what do we know about the conversion between cubic centimeters and milliliters? They're the same, right, perfect. So, this is 8.0 grams per milliliter. So, if we put that into our percent error, how do we do percent error? So,
Calculate volume minus accurate.
yeah, so Cooper got it there, calculated value, which is this right here, which we know is this, well, this right here, 8.0. Minus our value of brass, which is what?
8.0.
8.0. Divided by our correct value, which is again 8.0, times 100. So in actuality, you might have been off by a couple, but if we're using just these sig figs, 8.0 minus 8.0, what is that?
0.
0. 0 divided by anything is what?
0.
So percent error is
0.
exactly. There you go. So that pretty much means you're on the spot, is what that means. So percent error, 0. So, I did talk about this earlier, so what do you think percent error is a good representation of?
How far off you are from the.
Gotcha. So, is how far off you are from the correct answer. So we like to call that accuracy. So keep that in mind, remember that, keep it close to your heart. Basically, how close you are to something is accuracy. Now, not every one of our measurements was accurate, right? We had a little bit of percent error here, and we didn't have a 0 here, but like, some of you probably got 0.2, 0.4, something like that, right? So there's another measurement that we talk about, which is precision. So precision is consistency, exactly, right? So I like to think about it, let's see, so you do color guard, right? Does anybody do like sports or extracurricular activities, anything like that? Yes, what do you do? Cheer. All right, so we'll kind of keep both of those in mind. So with those practices, generally if you're trying to practice like a new formation or a new cheer, if you want to get it right, you don't just do it once perfectly and you're like, I'm done, right? You generally want to do it once and then you keep doing it right over and over and over again. So in practices, what creates good practice is not only accuracy, but also precision. Not only are you doing it right, but you're doing it right over and over and over again. So you're consistent and you're doing it right. So that's how you kind of think of the two. Precision is you're kind of repeated in the same area, so, and then accuracy is what you do right. Now you can have one or the other, right? So for example, I would say from these two volumes, so for the densities, would you say that the densities that we got are accurate? So technically, with at least one of us, we were accurate, right? So yeah, you were right there. So we're accurate in our density. Are we precise though? No, absolutely not, because we got a pretty decent bit difference here between the two. Does that make sense? So we were accurate because we did actually hit it, but we're not precise, right? You can also be precise and not accurate. Let's say if this percent error was 18.8%. Now, we're still off here, but would you say those are precise?
Yes.
Exactly, right? Because it's the same, it's pretty much on the dot for the same thing. Does that make sense to everybody? Kind of. Well, we'll do the, when we go to part B, it might make a little more sense because there's more points to deal with. So this one is kind of hard to see precision just because we don't have as many points to deal with. And generally with science and how we do calculations, you'll have more data points so you can see those trends a little bit easier. Right now we just kind of have the two, we're kind of comparing the two different densities. But with part B, it should be a little more clear. So I'm gonna go and erase this. So for part B, I want somebody to come up. Actually, what I can do is, let's see, I'm going to turn this, I think I'm going to use this so I can use their, so we're going to, there we go. That'll warm up, and then we'll go. That's fine. Do you think it'd be easier just to show one of their graphs on there so we can kind of talk about it? Yeah. Okay. So that's what I thought I would do there. And then I just need to go to source. Once it loads up, how much time do we have? We'll see. It should load up in quick enough time to kind of go over it, but let me check the part B here. Oh, there you go. Awesome. Cool. So, who wants to give me their graph that they used? No? No? Nobody feeling confident about their graphs? Let's see. I'm going to pick Eeny, Meeny, Miny, Mo. Does that work? Or I'm just going to choose Carson's. Alright, I'm going to grab yours real quick. And we'll go right here. Now, how do I zoom this out? It says right here? Oh, there we go. It says zoom out. Perfect. Okay, cool. So this is the graph we're looking at. So, first off, Taylor, how do we calculate the slope of this graph? 2 points where?
Well, you want to get them in between the axis.
Yeah, between the axis, but like which points do we want to grab?
On the line.
On the line, perfect, yeah. So we want to make sure, that's the reason we have the best fit line, so we can actually have a slope, right? If we just if we just connected the dots here, we would have a really, really weird line. So that's kind of the point of the best fit line there, right? So you get your points from the line, and then what do you do with them?
And then you calculate rise over run.
Rise over run, right? So we get 2 points. We start with the rise, the y-axis here. So you can kind of see that right here with what Carson did. Put a dotted line all the way to the top so she knows exactly how tall it is. And then we went out towards 7 there to kind of know how wide it is, and we'll get our slope here. So we don't have too much time left. So we're about to finish up here. But Carson, what did you get for your slope?
I think, I don't remember.
I will look. That's right, I have your work. So you got 1.24 in your slope. So we know that slope is in grams over milliliters. So again, what does the slope represent?
Rise over run.
Rise over run, right? But in the context of what we did here, we had grams on the left here for the rise. We have milliliters on the bottom. What unit is that? Density, right, perfect. So 1.24 grams per milliliters are density. So we're comparing this to the alcohol. So if we do a percent error calculations, you can kind of see it right here. Carson did a percent error, 1.24 minus 0.785 times 100, or over 0.785 times 100, gets us our 58.0% error. So for this one, is it accurate? No, there's a really big percent error. Is it precise? No, because we've got a line here. And the best fit line kind of helps us because we can kind of see that because we've got these points that are off the line. So if it was more precise, like all the points would be on the line. Does that make sense?
Yes.
And that's kind of a better show of precision because, you know, you've got multiple points, you can kind of see what's going on. Does that make sense?
Mm-hmm.
All right. Sorry to pick on your graph a little bit, Carson, but had to pick somebody. The one thing that you did good here is that your line started at 0, 0. And that's really important because, again, if you have 0 mass, you're probably not going to have any volume. 0 volume, 0 mass. So you can always count on 0, 0.